So let's take a look at vector functions. So a vector function is labeled as r of t, and let's say r of t has the components f of t, g of t, and h of t. Now keep in mind this can also be written as f of t times I plus g of t times j plus h of t times k. So yeah, it's basically the same thing, just written in unit vectors I, j, and k. So if we were to find the domain of the vector function r of t, we would have to find the domain of f of t, g of t, and h of t individually, and then we need to find a domain that satisfies all three of them. And so now let's say we're trying to take the limit of the vector function r of t. So the limit of r of t as t approaches some value a, let's call it a, is going to equal, in component form, the limit of f of t as t approaches a, comma, the limit of g of t as t approaches a, and then comma, the limit of h of t as t approaches a. So we have to take the limit of each individual component. And the same thing also applies to the unit vector form. We have to take the limit of each individual function, f of t, g of t, and h of t. So for number one, let's go ahead and find the domain of the vector function r of t equals t squared, the square root of t minus 1, and the square root of 5 minus t. So let's go ahead and start with the first function, t squared. Now the domain of t squared, if you think about y equals x squared, obviously the domain is going to be all real numbers. So t squared, domain is going to be from negative infinity to positive infinity. So now for the square root of t minus 1, obviously we cannot have the value under the radical be less than 0. So for the square root of t minus 1, we can go ahead and set it, or we can go ahead and set t minus 1 to be greater than or equal to 0. So in this case, if we add over the 1, t is going to be greater than or equal to 1. So that is going to be the domain of the square root of t minus 1. And now for the square root of 5 minus t, we can go ahead and set 5 minus t greater than or equal to 0, since once again we cannot have a value less than 0 under the radical. So if we go ahead and subtract 5, negative t is going to be greater than or equal to negative 5, and if I'm going to divide over the negative value, I must flip the sign, so t in this case must be less than or equal to positive 5. So that is going to be the domain of the square root of 5 minus t. So go ahead and put t is less than or equal to 5. So now once again, when we write the inequality for the domain must satisfy all three functions, so all three of these. So once again, the top one, t squared, is just negative infinity to infinity, all real numbers, so that doesn't really matter. But the domain here has to be greater than or equal to 1, but for square root of 5 minus t, the domain has to be less than or equal to 5. So t in this case has to be between 1 and 5. So that is going to be the domain. And if you want to write it in bracket form or in bracket notation, you can also write it like so. So now for number 2, let's go ahead and find the limit as t approaches 0 from the positive direction of cosine t, sine of t, and t times the natural log of t. So once again, if we're going to take the limit of this specific vector function, we must take the limit of each individual function inside the vector. So the limit as t approaches 0 from the positive direction of cosine t, well, we can just go ahead and plug in 0. Cosine of 0 is obviously 1. So that's going to be the limit. Now for the limit as t approaches 0 from the positive direction of sine of t, we can also go ahead and plug in 0. Sine of 0 is 0. So the first two functions are already done. Now let's go ahead and focus on t times the natural log of t. Now the limit as t approaches 0 from the positive direction of t times the natural log of t. So if we do direct substitution here and plug in 0 for t, obviously we'll get 0 here. So we get 0 times, now natural log of t as t approaches 0 from the positive direction is going to be negative infinity. So we get negative infinity times 0. And so negative infinity times 0, we don't know what that is because that's an undefined value. So what we have to do is go back to the function and sort of manipulate it so that we can use L'Hopital's rule. So if I take the limit as t approaches 0 from the positive direction. Now I can go ahead and bring that to the denominator, the t value, so we get ln t on the numerator and then over 1 over t. Now if I go ahead and plug in 0, we'll still get negative infinity on the top, and on the bottom, now as the t value gets closer and closer to 0, so let's say we have 1 over 0.000001. That's going to get closer and closer to infinity. So we'll basically have infinity on the denominator. So in this case, we have infinity over infinity, so we can use L'Hopital's rule. So when we use L'Hopital's, we're going to derive the numerator and the denominator. So the derivative of natural log of t is simply just 1 over t over, now the derivative of 1 over t, I can rewrite 1 over t as t to the negative first, so we can use the power rule, and we get negative t to the negative second. So I can rewrite it as 1 over t divided by negative 1 over t squared. So when I divide by negative 1 over t squared, I can multiply by its reciprocal, so t squared over negative 1. One of the t's will cancel, and so we're left with negative t. And so if I rewrite limit notation once again, the limit as t approaches 0 from the positive direction of negative t. So I can just go ahead and plug in 0, and then we'll get 0 for the limit. So the limit as t approaches 0 from the positive direction of the entire vector function is going to be the limit of cosine t, which we found to be 1, comma the limit of sine of t, which we found to be 0, comma the limit we found for t times the natural log of t, which is 0. So in component form, the limit is going to be 1, 0, 0 for a final answer. So for number 3, let's go ahead and find the limit as t approaches 1 of the square root of t plus 3i plus t minus 1 over t squared minus 1j plus tangent t over t k. So now it's in that unit vector notation where we have I, j, and k. And so it's still the same process. We're going to take the limit of each individual function here. So let's go ahead and start with the square root of t plus 3. Now if we take the limit as t approaches 1 of the square root of t plus 3, we go ahead, the first option is always direct substitution when evaluating limits. And so we'll get the square root of 1 plus 3, the square root of 4, which is 2. So that is going to be the limit. I'll just write it up here. Now the limit as t approaches 1 of t minus 1 over t squared minus 1. Now if we go ahead and plug in 1, we'll get 0 over 1 minus 1, which is 0. So that is going to be indeterminate. So you can use L'Hopital's rule, or you can also just simply factor and cancel. So t minus 1 we have on top, and then t squared minus 1 we can factor into t minus 1 times t plus 1. So in this case the t minus 1s will cancel, and so we're left with the limit as t approaches 1 of 1 over t plus 1. So we can go ahead and direct substitute now. So we'll get 1 over 1 plus 1, which is 2, so 1/2. So I'll write that up here. And now for the last function, the limit as t approaches 1 of tangent of t over t. So this is simply just direct substitution. So when I plug in 1 for t, we'll get tangent of 1 over 1, which is simply just tangent of 1. So that is going to be the limit of this function. So the final answer for the limit as t approaches 1 is going to be equal to 2i plus 1/2j and then plus tangent of 1 times k.